Hello, my name is James Baski and a graduate student of Memorial University. I'm here to give a quick presentation on advanced protection techniques that could be utilized in the renewable energy sector. Now, my presentation will mainly be focused on the IDMT. That's the inverse definite minimum time relay as a power protection technique that utilizes two distinct characteristics. So the presentation will give further details on this wonderful special relay. During the presentation, I will touch on the introduction. I would also touch on inverse definite minimum time relay, which is the main relay of question in this presentation. I'll touch based on the calculation notes, and I also ran some simulations that I'll go through during my presentation. Talk about the expected outcome and end the presentation. Now, in the world of renewable energy, where people are moving away more from the conventional power system and rather tying in renewable power sources into the conventional grid, the power system is subject to load fluctuations. And in saying that, we will then need a power system or power protection schemes or techniques that is able to quickly react on these variations, and we would want one that would react quickly when the load variation is so much, and one that would be less sensitive when there is a slight or very minimal variations. And in doing so, the IDMT has that characteristics to mitigate very high fluctuating loads. So when there are fluctuating loads that are too much and would tamper with the power system or would kind of disturb the power system, then this relay quickly reacts, But if it is a slight variation, one that is not so much of a disturbance to the power system, then this relay is a bit slow in terms of reaction and would react as soon as the variation changes. Now, talking of the inverse definite time relay, like I said in the introduction, the power systems are becoming complex, power systems are becoming larger, and as we are tying in renewable sources of power, it means that the system is bound to fluctuations. And in doing so, this IDMT relay usually has two distinct characteristics. The first is the inverse characteristic. So whenever the quantity in question, let's say current, increases, okay, let's take this graph. So when the current is small, okay, you realize that we have a higher response time, meaning that the relay would take a longer time or period to react. Whereas when we have a higher current, this relay takes a relatively shorter time to react. And that is the inverse characteristics of this IDMT relay. Now, The second characteristic of this relay is a definite characteristic. So when the current increases beyond a certain threshold, the relay response period is almost constant. It doesn't really change. So as this curve projects in a constant manner, the response time will also be constant, and that is what this relay does. So irrespective of the magnitude of the current, at a certain point the relay would react at a constant time period, and that's the beauty of this relay. In terms of calculation note, of course, we are using a line voltage of 400 volts and a peak fault current of 710 volts. Now, I would touch on the trip time for the instantaneous overcurrent relay. So, the total time for the trip signal includes the time at which the fault is applied, that's TFA, the time taken for the IDMT relay to operate, plus the delay due to mechanical movement of the relay. So in our simulations, you are going to see that the time the relay indicates in the simulation is slightly different from the waveform, the time per the waveform, and this is because of these two trip times, these other times. That's the time the fault was applied and the time due to mechanical fault. So just keep note of these during the simulation discussion. So on the schematic for the protective relay, our relay has a voltage sensing, current sensing, ground fault sensing, and temperature sensing abilities, where whenever there is a overcurrent or undercurrent, the relay senses this fault. It issues a trip signal to the CT for the CT to trip and conveniently take out the fault from the system, which is where the system is later restored when this fault is cleared. Okay, so the idea is to protect whatever loads we have connected to the power system, and this relay works in conjunction with the circuit breaker to help achieve this coordination. Now, for scenario 1, we considered a relay setting such that we considered the lower setting as 5 amps as per our calculation, and the time multiplier settings as 1, and the higher settings was 6 times the current multiplier. So for the CT, the primary setting was 100 amps, and of course the secondary, which is standard, is 5 amps. So whenever there is a 100 amps fault or current, the CT should record a 5 amps on the secondary side when we measure the secondary out or the output. Also, we are using 50 Hz for this setting. So scenario 1 happens to be our benchmark, and we use that to ascertain or measure the performances of the relay. So this becomes our benchmark, and in doing that, we recorded a trip signal or a trip at 4.29 seconds, and this is the relay trip time, the actual relay trip time. But when we consider the trip time due to the mechanical movement of the relay, we realize that the relay actually tripped at 4.50, or 4.5, at least around 4.5 seconds. Yes. So that's being our default scenario. Let's move to scenario 2. So in scenario 2, we changed the TMS, which is the time multiplying settings. We kept this constant. We kept the lower settings of the relay also constant. All other things remained constant. But when we change the TMS or the time multiplier settings, we realized that the relay trip time was 2.145 seconds, which translates to about 2.36 seconds, and which, like I explained earlier, was due to the time due to the mechanical movement of the relay. Okay, so what then happens when we increase the relay current further, or the fault current further? So that is answered in scenario 3. Scenario 3, basically, we changed the TMS further from 0.5 to 0.05, and the higher current, the multiplier, we even multiply the current output by 10 times to see how this would behave. So if our current is 10 times larger, how would the relay behave? And as we expected, the relay trip time reduced even further from 2 seconds to 0.2 seconds, which is really fast. At 0.2 seconds, which is really fast for such current magnitude. Now, these 3 scenarios elaborate on the inverse characteristics of the relay, where we increase the current and the relay time reduces, or the relay response time or the trip time reduces significantly. Now, scenario 4 tells us a different thing, or a different story. So when we go to scenario 4, we realize, for the changes, we kept the low settings, we kept the TMS, but we increased the to the maximum, to infinity. We increased the highest current settings to infinity, and we realized that the relay response didn't change. It remained constant. It means that irrespective of how high the current may be at a point, the trip response time remains constant. And scenario 4 gives or ascertain the fact that we would get a definite response time after a certain period. So this scenarios, or scenario 1 to 3, evaluated and really proved the inverse characteristics of this IDM relay. And scenario 4 also evaluated and proved the definite characteristics of the IDM relay. This relay, I believe that when instituted in or incorporated in our power systems, in these modern power systems where there are fluctuations and current changes here and there, it would be able to do proper biasing. The relay should be able to sense fault currents and properly operate when it is supposed to operate, so that we do not want to have relays that are operating even when we have false current. We just have a short changes in the current form. We would want to have the relay tripping when we have higher current, or when the fault current is increasing exponentially. But when the fault current is minimal or very small, we do not have a relay false tripping and putting up the system, which makes the power system unreliable. We want a reliable power system, and hence I believe this advanced protection technique of relaying would be a better substitute to the differential relays, where it would utilize the inverse features and the definite features to properly protect or isolate the power system in terms of fault. So the projected outcome was fully achieved, and like we said, the first simulation indicated the inverse characteristics. It proved the inverse characteristics, and the last one exhibited consistency, where we got a definite or a constant trip time, relay response time, even when the current was set to infinity. In terms of conclusion, we succeeded in ascertaining both the inverse and definite characteristics of the IDM relay, and I believe that this relay technique would help our power sector, our power systems, especially now that we have very tricky, impulsive power system, where we have load we have power, we are receiving power, or we are tying into our grids with different power characteristics. This idea relay would properly operate at the right settings. This brings us to the end of the presentation.